Okay, so let's start today's class. And um, can you see the screen? Can you see the screen?
Yes, sir.
All right. So the thing is, we in the last class we are talking about the covariance, and we talked about correlation, and also we have seen this theorem 4.16. In the theorem 4.16, we have already seen these three definitions, or you can say three theorems, and those theorems actually are some relations between these covariance and correlations, and actually also the different variance and mean values. Okay, so from that we have also seen one example 4.12, and in this 4.12 we were supposed to find out the correlation value and the covariance value, and in the solution we have found out the correlation value first by using this expected value of x and y, and then we have talked about this ex and uy, and we have found out the covariance of xy, because we know that the covariance of xy is the correlation minus ex into uy. Okay, so I think you can remember the last class. Now today, yesterday also we talked about this orthogonal random variables and uncorrelated random variables. I told you that even if the correlation value equals to 0, we cannot say that they are uncorrelated. We will say that they are orthogonal. But when we can say that they are uncorrelated, when their covariance value equal to 0. Okay, so keep in mind that that when the correlation value equals to 0, then they are orthogonal, and when the covariance value equals to 0, they are uncorrelated. All right, then today we will talk about this correlation coefficient. The correlation coefficient of two random variable x and y is given by this formula. Look at this: rho xy equals to covariance of xy divided by root over variance of yx and variance of y. That is actually individually, if I say that they are actually standard deviation multiplications of x and y. Okay, so if somehow we can find two random variables covariance and their individual variances, then from that we can find out the correlation. Okay, and this is the correlation coefficient, how much they are correlated. It can be actually this value can be actually from -1 to +1. When I'm talking about that the correlation coefficient is 1, that means they are fully correlated. Fully correlated means positively correlated. That means if one increases, another one also increases. Okay, but when I'm talking about that this value is -1 means they're fully uncorrelated, and definitely when one is increasing, the other is decreasing. Okay, so this correlation coefficient actually gives us an idea about those two random variables and how they are interrelated with each other. Now, if I increase one random variable, what will be the effect on the other random variable, that we can understand. Okay, is there any question regarding correlation coefficient?
No, sir.
Okay, so this correlation coefficient we have understood. Now we will understand another issue, that is independent random variable. Okay, what is an independent random variable? Remember one thing, these terms are very important: uncorrelated, orthogonal, independent. Huh? So independent is another important issue. When can we say that two random variables are independent? We can say that if and only if this is true. What is that? Their joint probability will be equal to the marginal probability multiplication. If I'm talking about x and y, two different random variable, then we are having a joint probability of xy, and this joint probability will be equals to the individual, or you can say the marginal probability multiplications. Okay, so this is a very important thing. So this I mean, in a discrete case, we can say that Pxy is the joint probability, or you can say joint PMF. This is the joint PMF. So that case, joint PMF will be individual PMF multiplications. And in the case of continuous random variable, this joint PDF will be equal to the joint individual PDF multiplication. Okay. So to understand more about this one, let's see one example. Example 4.23. Okay. The example 4.23 says that we have a joint PDF. So we are talking about a continuous random variable. So it is a joint PDF, which is equals to 4xy. And the x limit is from 0 to 1, and y limit is also from 0 to 1. And they're telling that are x and y independent or not. Okay. So we know that for finding the independence, we need to find this formula. What is that? F of x, y, that one has to be fx into fy. Okay. So this has to be true to find out the whether this x and y are independent or not. All right. So this independent or not, remember one thing, that what we have already this joint PDF. It is already given. What is not given? Marginal PDFs are not given. So we have to find it. How do we find the fx x from this fxy? We know if I integrate all the y value from minus infinity to plus infinity, then actually we can find out the PDF of x. We know that. Okay. So this y limit, actually y is limited to 0 to 1. So if we make the limit actually 0 to 1, because outside that limit there is no value for joint PDF. Even if we give minus infinity to plus infinity, actually that limit will be reduced to 0 to 1 in this range. Okay. So we can write it 0 to 1, and this joint PDF value is given, it is 4xy, and then dy. So when I'm talking about dy, then actually y is a variable, x is not a variable. So 4x we can take it outside, and then integration of y dy 0 to 1. And if we do that, we know that integration of y is y square by 2, and then put the values of 0 to 1, and this 4x is in front. Then we can write it something like y square means 1 square minus 1 square means actually this is y square by 2, so 1 square by 2, that is half, and then minus 0, so that will be 2x. Is it okay?
Yes, sir.
All right. So this is how we have found out the fx. Now how to find out the fy? Let's do it. Fy equals to similar, minus infinity to infinity, this uh, the joint probability. Now it will be what? Dx, isn't it?
Yes,
So
sir.
this x limit is given also 0 to 1. So similarly, that will be also 0 to 1, and that value will be again 4xy, and then it is dx. Now the variable is x. So x cannot be taken outside. So we can say that 4y can be taken outside. So this is equal to 4y integration of 0 to 1 x dx. So that part actually the same as this part, isn't it? This part is the same as that part. So that result is half. So this will also be half. So we can say this 2y. Is it clear?
Yes, sir.
All right. So we have found out 2x and 2y as the fx and fy. So this let's check whether fx into fy, what is the value? That one is 2x and that one is 2y, and combined it is 4xy, which is the same as this joint probability. Look at that. This is the 4xy, isn't it? So now we can say that the marginal probability multiplication is the same as the joint probability. These two are same. So if we can say that these two are same, then actually we can say that they are independent.
Independent.
Okay. So the independent criteria is the multiplication of individual probability or the multiplication of the marginal probability that will be same as the joint probability, even if it is in the discrete case or in the continuous case. That is true. So we have seen one example by which actually we can prove that this criteria is solved, or that criteria is proved. That's why it is independent. Is there any question regarding independence? Any question?
No, sir.
No question. Let's clear and go to the next slide maybe. So we have also already seen this one. We've already seen this one. Hmm. So now in the theorem 4.27, they are telling that when the x and y are independent, then for them we can draw this, or we can write this, these six criteria. Okay, these six criteria. What are these criteria? That expected value of gx and hy, or we can say the function of x and function of y, if I multiply them and make the expected value, that will be the individual expected value of those functions of x and y. This is number one. Number two is, we know that this correlation is the expected value of x into y, and then that value will be equals to e of x into e of y. Okay, so we already know that the correlation value is equal to expected value of xy, but that value will be individual expectation for independent random variable. As they are independent, so we can individually multiply the exy. Okay, and then we are writing that covariance of xy. I already told you that this correlation coefficient equals to what? Correlation coefficient equal to covariance. Have we talked about it? Yes. Covariance of xy divided by root over variance of x into variance of y, isn't it? So if it is like that, when I'm talking about this correlation coefficient, remember that one, that this covariance value will be equals to 0 when the when it is independent. When x and y value are independent, then we can say covariance will be equals to 0, and actually we can say that they are uncorrelated. And they are uncorrelated means they will have no dependency on other x on y. So the thing is, covariance equals to 0 if the x and y are independent, then this covariance will be 0. And if the covariance is 0, then definitely this rho xy will also be 0. That's what it is mentioned here. Okay, so the thing is, if it is independent, then the covariance value will be equal to the rho value, will be equal to the 0. Rho value is equal to what? Rho value is the correlation coefficient. I told you already. Correlation coefficient. Okay, so this is the correlation coefficient, and we can write it like that. Now another issue is D. Look at that, variance of x plus y. Can you remember that equation? Variance of x plus y was equals to variance of x plus variance of y plus 2 into covariance of xy. Can you remember? So if you can remember that equation, as this covariance value is equal to 0, so we can cut that part, it is equal to 0, and then there will be only variance of x plus variance of y. This is true for the independent random variable x and y. That means x and y, if they are independent, then we can write this. Okay, then this expected value of x condition y will be equal to expected value of x. We can understand x condition y. What does it mean? It means it's a conditional probability. If I say that the probability, this is the conditional probability. Conditional probability of x when y has happened. Now the thing is, y is influencing x to change the probability. But if y and x, if they are independent, then actually there is no influence of y over x, and actually we can say that they are uncorrelated. There is no relation between x and y. So if there is no relation between x and y, whether y happens or not doesn't mean anything. That's why x condition y is the same as x, normal x. So probability of x condition y will be equals to probability of x. Similarly, expected value of x condition y will be equals to expected value of x. Okay, so this is the idea, like this, that expected value of x condition y will be equals to expected value of x. Directly we can say that, because there is no relation between x and y. Similarly, look at that in the case of y condition x, same as y condition x means expected value of y. So the thing is, this expected value of x and expected value of y, we can directly write like this one. Okay, so these are the 6 criteria that we have to keep in mind. That if x and y are independent, then for them we can write these 6 criteria. Actually these are some 6 simplified equation for independence or independent random variable x and y. Is there any question? Is there any question?
No, sir.
Okay, so let's go to the next slide. All right, let's solve this example. Example 4.25. Okay, so the thing is, here it is given that the random variable x and y have a joint PMF and given by the following matrix. So like a joint PMF is given for different value, like x equal to -1 and x equal to +1, and then y equal to -1, y equal to 0, and y equal to 1. So there are 6 different probabilities are given here. Okay, now the thing is, they're telling are x and y independent, and again are x and y uncorrelated. Remember one thing, for independence we have a very rigid equation that we have to think about. Okay, that is when this p of xy will be equals to px into py, then I can say that they are independent, isn't it? For independence we have a very rigid equation, I mean rigid criteria which have to be followed by this um, joint probability or joint PMF and marginal PMFs. Now the thing is, we have this joint PMF. If we can find out the marginal PMF, then actually we can uh, we can solve it. Now the thing is, remember one thing, this joint PMF for different point is given. Now if for a single point If the criteria is not met, then we can say that it is not satisfying the criteria. All right. So the thing is, when we are talking about this joint PMF, like PXY, say for example, the first one, let's start with the first one. That is x equal to -1 and y equals to -1. So x equal to -1 and y equals to -1. This joint probability PXY equals to what? Equals to what? Equals to what?
Sir, 0.0625.
Why? I'm talking about the point x equal to -1 and y equal to -1. This is a particular point. That particular point will have a particular uh, uh, probability. This is the probability for different points. It's a matrix form. When I'm talking about x equal to -1 and y equal to -1, that means what? First row and first column. In the first row and first column, which is the what is the value?
0.
0 is the value. So this 0 is the joint probability for this particular point. There is no way that it will be 6.25, something like that. Okay. So when I'm talking about a particular point, say for example, x equal to 1 and y equal to 1, what is the joint probability? It is given, it is 0.25, isn't it? So let's find out the this equation, whether it is right or wrong for a particular point like x equal to -1 and y equal to -1, and joint probability is 0. So if I can find out that px into py, that one will be equal to 0, then I can say that this is satisfying. And then point by point, I have to find out all these criteria, whether they follow or not. If for all the points they follow it, then I can say that this is an independent case, or you can say x and y are independent. But if any one point we find that they are not equal, then I can say that they are not independent. Okay, then let's find out the px for this particular point. So px for x equals to 1 -1 what is the probability? Can you say that?
0.5.
0.25, because it's 0 plus 0.25 plus 0, that will be 0.25. What about py, y equals to -1?
The same.
This is again 0.25, because we are adding these two we are adding. Okay, so if I multiply, of course we can see easily that they are not equal to 0. Okay, they are not equal to they are not equals to 0. Of course there will be something different, and that is not equal to this 0. So we can say that x and y are not independent. We don't need to check others, and we don't need to check the other form other points, because the starting point we have taken a decision, because they are not following this criteria. Independent. Is it clear?
Yes, sir.
Okay. Now the thing is, are x and y uncorrelated? For x and y to be uncorrelated, what criteria has to be met? Tell me.
Covariance 0 হতে হবে.
Covariance 0 হতে হবে, right? The covariance has to be 0. So the thing is, if the covariance equals to 0, then what we have to find out? We know that the covariance equals to what? Covariance equals to probability of what was the covariance equation? covariance was something like কিভাবে করবো বলো? কোভেরিয়েন্স বের করার সূত্রটা কি ছিল? কোভেরিয়েন্স আমরা জানি যে ইটা আমি এই রো ইনটু সামথিং, এটা তো হবে না। Covariance, we know that the covariance will be equals to what equation? We need to find out the covariance. Okay, let's see. Let's check. And they have okay. Covariance was, I can remember now. Covariance was expected value of xy minus ex into ey. Can you remember that one?
Yes, sir. Yes, sir.
So covariance of xy equals to expected value of xy minus ex into uy. So if we want to find out the covariance value, then we need to find out this expected value of xy and then expected value of x into expected value of y. So all these values we have to find out. Okay, so if we need to find out all these values, then we need to go for a exclusive findings. Look at that. They have easily given a e of x equal to 0.5. Now how this e of x equal to 0.5? We need to find out the px, isn't it? Okay, no problem. We know that e of x equals to x px summation, isn't it? This is the single valued case, x px summation. Okay, and we know we can find out this px like this. For x minus 1, this is 0.25. For x1, it will be 0.75. So px we have found out. What about py? Py will be, this is 0.25, this is 0.5, this is 0.25, isn't it? So if we have found the px, so this ex can be found out 0.25. Sorry, this is x is minus 1 into, for minus 1 the probability is 0.25, plus, then for plus 1 probability is 0.75, and then it is minus 0.25 plus 0.75, and that will be 0.5. So from that they have found out this px equal to 0.5. Can you understand? Can you understand my logic? I need the feedback.
Sir, can you repeat?
Okay, this is a joint probability, and the joint probability is given. From joint probability we know how to find out the marginal probability, isn't it?
Yes, sir.
This is one marginal probability px. How to find out? For x minus 1 we will add all the x, all the y. This one we have made a sum and we have found 0.25. For x equal to 1 we will add all these y probability and sum, we have found 0.75. This is the way how to find out the
Sir, I understood. Like you summed it and then
right.
yes, sir. I
So-
was confused there. Okay.
So this is the marginal probability of x. How to find the marginal probability of y? Add
So we add those values of x.
add those
probability
two
of x.
values. This is the value. Add those two values. This is the value. Add those two values. This is the value. Okay, so we have found out the px, we have found out the py. So from px, if I have the px value and also the x value also we have, So if for x equal to -1, px equal to 0.25, for x equal to +1, px equal to 0.75, and we can, if I sum, then we can find out the 0.5. And for py, if I want to find out the ey, how to find out the ey? Ey equals to y into py summation. Y is how many? 3y. So for -1, the value of probability is what? 0.25. Can you follow?
Yes, sir.
Then for y equal to 0, it is 0.5, 0 into 0.5, then plus 1 into 2.5, plus 1 into 2.5. What is the result? That is already 0. Then minus 0.25 plus 0.25. That is equal to 0.
Yes, sir.
That's why this ey value has come to 0. What about the exy? For exy, we can have the six cases, but because for xy, we have to find out, for exy, we have to find out the x into y into pxy, isn't it? And that will be equal to what? -1 into -1 into 0, 0, isn't it? Plus -1 into 0 into 0.25. This one, -1. I mean, for all these 6 points, we have to find out the corresponding x value and y value and pdf value. Three things.
Understood, sir.
Okay. And then this is 0. We don't need to write out. Okay. And that one is -1 into +1 into 0.25, and then this is 0 because y value is 0. We don't need to write. That one will be what? 1 into 0.25. Actually, this one is 0, this one is also 0. So there are only two values. And then this one is -2.5 or 0.25, another one is plus 0.25. So that value will be equal to 0. Is it clear?
Yes.
So this E of xy is 0 from this one. Now, if I want to find out the covariance value will be 0 minus E of x is 0.5, and then ui is 0. So that will be equals to 0. So the covariance value is equals to 0. So covariance value equal to 0 means they are uncorrelated. Okay. Okay. So
Yes, sir.
the thing is, we have this different values, and from these different values, we have found out they are not independent, but they are uncorrelated. How will you describe this one? We know that if the values are independent, their covariance equal to 0. But here we have found that they are not independent, still their covariance equals to 0. How can you explain this one? Explanation is covariance equal to 0 is not a criteria for independence. So if x and y are independent, that doesn't mean that the covariance will have to be 0. Okay. I mean, sorry. If the covariance is 0, doesn't mean that they have to be independent. But if they are independent, the covariance value must be equal to 0. So we can say that all the independent random variable will have covariance equals to 0, but all the covariance equals to 0 doesn't mean they are independent. It's a very good question actually. It's a very good question for the for the final. Okay, so keep in mind that all the independent random variable, the covariance must be 0. But if the covariance is 0, doesn't mean they are independent. Okay, any question? Any
No, sir.
question?
No, sir.
No question. So I think this is the last slide of this chapter. Uh, so they are uncorrelated. So I think this is the last slide. Um, that's the end of chapter 4. Okay. So actually, previously it was up to the syllabus for me, but now we are behind actually. Okay, so let's go for chapter 5. In chapter 5, we are starting with this random vector. Random vector. Okay. Can you see the slide? Random vectors.
Yes, sir.
All right. So in the random vector, the introduction is, look at it, n random variables in terms of an n-dimensional CTF. Remember, previously we talked about two variables like x and y. This chapter is about n number of variable. If we have x, y, z, a, b, c, d, e, f, g, h, like this number of variable, then we can say that that particular idea is in this chapter. So we are talking about now n random variable in terms of n dimensional CDF and n dimensional PMF and n dimensional PDF. Okay. And then the marginal probability functions of subsets of n random variable. The marginal probability also can be found out like this. Then n independent random variables, independent random vectors, and expected values of functions of random variable. So actually we will see all these things. And then covariance matrix and correlation matrix. Now previously we talked about the covariance value, but now we will have some covariance matrix, not a single value. Say for example, I'm talking about x with y, then x with a with b with c, like that. So many combinations are there. That's why covariance value will not be a single value like before. Now the covariance value will be a matrix. So the complexity actually increases in n times. Okay, so these actually will um, we will think about it in this chapter. We'll start with a multivariate joint CDF. So already we know about the joint CDF. We talked about the fxy. Now we will talk about the fx1 y1 x1 x2 x3 up to xn. So this will be, remember one thing, that when I'm talking about this I mean joint CDF or multivariate joint CDF, now the dimension is not 2-dimension. Previously it was 2-dimension and a point we have found, and this x value less than x, y value less than y, we have found it like that. But now when I'm talking about n dimension, then actually it cannot be drawn in the figure. You have to understand that it's a point with n dimensional case, and from the particular point x will be, or x1 will be less than x1, x2 will be less than x2, x3 will be less than x3, and xn will be less than xn. Okay, so this is a multivariate joint CDF. Now the PMF, joint PMF, look at this PMF. This PMF actually is the similar kind of thing that previously it was less than that one, but now it will be equal to this one, equal to x1, equal to y1. So actually we are pointing a particular point. That one is particular area. Now we are talking about particular point. So this is can be a joint PMF. Also, we can talk about the multivariate joint PDF. Understand that PDF we have to find out from the multivariate joint CDF. Directly we cannot say that what actually PDF is. You can understand. Remember one thing, because PMF can be pointed out, but PDF cannot be pointed out. Because PDF actually is a kind of slope. And from the CDF, we can find out this PDF by using differentiation. By n-dimensional partial differentiation, we can find out the multivariate joint PDF. All right. Now we have a quiz 5.1. You try to see in the room, I will say. Okay. Now I'm talking about this random vector probability functions. Random vector probability functions. And, and these random vector probability functions are this CDF will be fx like this one. I told you already that if it is n dimensional, actually we can say that this is a vector. When I'm talking about n dimensional something, we can actually talk it about the vector. So they are talking about this is a random vector. Now another thing is, if I say that x is a vector, another vector y can be there, and like a joint CDF like x and y. Previously we talked about two random variable x and y. Now we are talking about two random vector x and y. So x is one vector under which there are n number of random variable present, and y is another random vector under which there are m number of random variable present. And if we want to find out the joint CDF of x vector and y vector, we can find out by using this one. So you are going more complex. Okay, so it's a joint CDF, joint PDF, and joint PMF. All can be there. Okay. Now let's see how an example can be solved. Actually, we are not going in detail about all the things because in the previous chapters we have seen many things about the variance, covariance, this. Yes, we will also see the covariance, because covariance is now not a single value but a matrix. So we will see that. But the other things we will not go in detail. Look at this. If there is a random vector x has a PDF like this. Now, how to solve it? What's the time now?
320.
20. Okay, let's see. Look at this one. We are having this A equals to 1, 2, 3 transpose. Do you have any idea about transpose? 1, 2, 3 transpose.
Row column হয়ে যায়, column row হয়ে
Right.
যায়।
So the transpose actually will become the same as this 1, 2, 3. And if I may say this is A, if I say A transpose, then that will be what actually? Double transpose means actually that will be the same as 1, 2, 3, isn't it? So here it is written A transpose, and the A value is this transpose. So actually this will be whatever here, same as this one. That means that will be minus A means 1, 2, 3 into x. X actually is what? X actually is a vector. As there are three values, so we can say this is a 1 into 3 matrix. So the x value should be a 3-into-1 matrix for multiplication, isn't it? And that will become 1-into-1 matrix. So if this is a 3-into-1 matrix, that means X actually is a vector, definitely vector. We will write the vector like this. Okay, so that will be 6 e to the power minus 1, 2, 3, and the X can be written as something like x1, x2, x3. Okay, and then that can be written as e to the power minus x1 minus 2x2 minus 3x3 and then 0. Okay, so this PDF can be written as like this. Now what is the CDF of X? CDF of X means we have to differentiate, we have to integrate the PDF and find the CDF. So the CDF of X should be the integration of this 6 e to the power minus x1 minus 2x2 minus 3x3, isn't it, dx? Do you agree with me?
Yes, sir.
All right, now this is your work. That one actually is what? That one actually is e to the power minus x1 into e to the power minus 2x2 into e to the power minus 3x3. Okay, so you have to integrate and find out the result. All right, can you do it?
Yes, sir.
I think you can do it. These integrations are means individual integrations before 6, and then we know that the limit of x is equal to, it's given, I think. What is the limit of x?
So
X is
minus
more than
infinity
0.
to 0.
X is more than 0, so we can say
0 to plus infinity.
0 to infinity. Okay, so you put the value and you can find out how it works. Okay, so let's see what is the result. They have found out this one and they have found out the result, 1 minus e to the power x1, 1 minus e to the power minus x1. Okay, we put the value of 0 and then you will find out the result. Actually, remember one thing, in this particular case we are not actually putting the value of x1 equals to infinity, we are putting up to x1. Remember one thing, this is this integration. Say for example we have 6 and 0 to infinity, actually up to point x1 we need, because this is a CDF. CDF means up to point x1. So up to, say this one is something like e to the power minus x1 with dx1, and if I integrate this one, what comes? E to the power minus x1 will be e to the minus x1 with a minus sign, and that will be with from 0 to x1, and if I put this e to the power 0 minus e to the power minus x1, and that will be 1 minus e to the power minus x1. So that minus will be there in the previous. So that actually is same value with this value. Okay, so you can, if you do it, you can find out how to solve it. All right, you can do it, isn't it?
Yes, sir.
Okay, so let's go to the next slide. Marginal probability functions. So the marginal probability functions, this is coming like this. When I'm talking about this, this probability, that is probability of XYZ from WXYZ, we have a joint probability of 4 random variable WXYZ. Now, when I am ignoring W, I mean, when I'm trying to find out probability of XYZ, that is 3 random variable probability from a 4 random variable probability, that means we have to summation, we have to take summation of all the values of W, isn't it? When I'm talking about this WZ, then I'm talking about taking X and Y. All right. When I'm talking about this, I mean, say for example, from 4 random variable to this 2 random variable case, then we are actually we are actually making a sum of those extra 2 random variable. Say for example, from WXYZ to W and Z. That means I'm actually ignoring this X and Y. So I have to take both summation, that is double summation of X and Y, like this. Okay. And then if I want to find out the single random variable X from that 4 random variable WXYZ, then actually I have to make 3 summation of those W, Y, and Z. W, Y, and Z. Okay. So how many random variable we need in the outcome, that will be dependent by, or that will be determined by the number of summations. Say I want to take from a 6 random variable to a 3 random variable, then how many summations will be there? Tell me.
6 to 4.
6 to 3.
Oh, 3.
3, because the difference is 3. If from 6 random variable I want to make a single random variable case, then how many summations we need?
5.
5 summations. Very good. So this is the way actually we use this, I mean, the marginal probability. We can find the marginal probability from the joint PMF. Is it clear?
Yes, sir.
Okay. Now that was the joint PMF. Similar kind of thing can be done by using a joint PDF. Okay. So the thing is, the joint PMF and the joint PDF are almost similar. Just in the joint PMF, we are using the summation. In joint PDF, we are using the integration. Okay. Now I think we have to solve one example. Example 5.5. Let's solve it. How to solve it? We have been given an example 5.5, which is actually the joint PDF is given, and that PDF actually is a 4 random variable PDF. And this 4 random variable PDF, we are having this value given, and also we have been given the limit. Okay. So, and we are also given a task to find out the marginal PDFs, and this is 1 4, this is 2 3, and this is 3. Now remember one thing, when actually, say for example, I have found the F2 3 or FY2 and Y3, then for finding the FY3, we don't need to triple integrate this 4 random variable. We can use this one, and by using a single integration, I can find the FY3 from FY2 and Y3, isn't it?
Yes, sir.
So we have to understand how actually the marginal probabilities can be found out. How many integration do we need? If we have a lower integration work, then why will we go for the upper kind of thing? So this is the um, joint PDF of this case. Now let's find out first Fy1 y4. Okay, so what is the y1 y4? Fy1 y4, that will be what? That will be definitely double integration. Okay, and this f1 this joint probability is 4, so we can write here 4, no problem. Now what integration we are doing? We are keeping 1 and 4, so we have to integrate 2 and 3, isn't it?
Yes, sir.
So if it is 2 and 3, look at this one. Y2 limit is what? Y2 limit is from y1 to 1. Y1 to 1. What about this y3 limit? It is 0 to y4, isn't it?
Yes,
So
sir.
if we if we start from I mean, if this is the dy2 and dy3, then the first limit is y2, that means y1 to 1, and then the second limit will be for dy3, that is 0 to y4, 0 to y4, isn't it? So how can we do that? Look at this, 0 to y4, and that one will be a fixed value 1, say for example 4. So 4 means it will become 4x, isn't it? Because x to the power 0 plus 1 divided by 0 plus 1, that is
Sir,
x.
does it matter in which sequence we integrate? Like if we want to do
Actually I want to see that one. I'm not sure in the book what sequence they have done.
right, sir.
I feel that that should not be a problem. So the thing is, that one is becoming 4y with a limit y1 to 1, and then dy3. So if it is 0 to y4, then that will be 4 minus 4y1, or we can say that 4 into 1 minus y1, isn't it? And then dy3. And then if I do that, 4 into 1 minus y1, then actually it is the dy3 is the thing, so that should be y4 minus 0. So actually it will be 4y4 into 1 minus y1, isn't it?
Yes, sir.
So if it is like that, let's see what they are doing. Okay. Oh, they are they have so this is our result, that is their result. They have also done in the same sequence, maybe. No, they haven't done in the same sequence. They haven't done in the same sequence. Look at this. Look at this. They are doing sorry. They are doing it. Look at this one. The green one is the previous slide, and they have done it 0 to y4 and then y1 to 1. But we have done first y1 to 1 and then 0 to y4. And the result actually is same. 4 into 1 minus y1, 4 into 1 minus y1 into y4. Have you seen this one?
Yes, sir.
Okay, so the result actually is same. The result is same. So this is for y1 y4. All right, this is for y1 y4. Similarly, because we don't need to calculate all these in the class, this is done. Okay, this is done in the class, and then similarly I can say, actually this is a probability. I mean, this is a probability, not a PDF. So for PDF we need to find out in this format. And remember one thing, when I'm talking about this limit, and now actually it is variable is y1 and y4. Previously the limit actually is with y3, y2 as well. But when I'm talking about this y1 and y4 only, then y1 is from 0 to 1 and y4 is only 0 to 1, because there is no y2 and y3 now. So y2 and y3 you can omit, and directly you can find the limit from that given limit, and it is 0 to 1 and 0 to 1. Okay. Similarly, we can find out this one as well. We don't need to go for calculation, isn't it?
Yes, sir.
So the thing is, for y2 into 1 minus y3, we can find out like this. And now the important thing is, that is a PDF now. Now from this one, if I want to find out the f of y3, for finding this one, what we have to do? We have to find the limit of y2. This is for y2 into 1 minus y3. And this limit of y2 will have to be given. Y2 limit is from 0 to 1, because we are actually integrating with y2. So that particular part is now a constant, and we have to integrate this one, isn't it? So if we do
Yes.
it, then 1 minus y3 can be taken outside, and then this 4 into y2 square by 2 with a 1 0 limit. I'm not sure whether my calculation is right or not. 1 minus y3, then this 2y2 square with a 1 0, and then we can write 1 minus y3 with this 1, that is 2, minus 0, that is 2. So this one is should be there. Did you understand?
Sir, previously for the upper bound values, we have used y1, y2 like that, but this one we have used actual upper value. Why?
Remember one thing, now there is no y2, there is no y1, y1 or y4. The limit is now this one. This is the limit now. The limit
Oh,
previous,
okay, okay.
the limit is
Previously it was assigned as y1, y2.
right. Previously it was assigned like y1, y2, like something like that. But now
Okay.
it's not assigned like that. Now the value of y2 doesn't depend on the value of y1 or something like that, because there is no y1 here.
Mm.
Okay. So
Yes.
so look at this. So we can actually do it like this: 2 into 1 minus y3. Let's see the result. I'm not sure. 2 into 1 minus y3. Well, yes. So we have got the original answer. So we have get this 2 into 1 minus y3. All right. So the thing is, by this way actually we will solve our equations, and this is the probability. Just to show that PDF, we are using this one. Now look at this. There is no limit about y2, because we have already made a sum of y2, and we have cleared y2. So the limit will only be for y3. Is it clear?
Yes, sir.
So is there any question about this this problem?
No, sir.
Okay. So if there is no problem, then how much time it is? Maybe we can stop it
3:40.
here. Okay, maybe we should stop it here. All right. So let's stop it in this independent random variable. And if you have any question regarding today's class, you can ask.